Hi, so this video is over section 5.3, which is over independence and the multiplication rule. So we have three learning objectives. We want to be able to identify independent events, use the multiplication rule for independent events, and then compute what we call at least probabilities. So in objective one, we have here to start with the definition of independent and dependent events. So two events E and F are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. So two events are dependent if the occurrence of event E in a probability experiment affects the probability of an event F. Right? So in other words, two events E and F are independent if knowing what happened in E doesn't impact the probability of F. Right? So I have here an example of going over some situations and if, are these independent or not. So A says, suppose you draw a card from a standard 52 card deck of cards and then roll a die. The event draw a heart and roll an even number are independent because the results of choosing a card do not impact the results of the die tossed, right? So no matter what card I pick, it's not going to influence what I roll when I roll the dice, right? Those two things are not like related, right? They don't depend on each other. So these are independent, right? And then part B, it says suppose two 40-year-old women live in the United States are randomly selected. The events woman 1 survives the year and woman 2 survives the year are independent, right? So I want to go over what that one says, and then if you look at part C, it's very similar, except it says they live in the same compartment complex instead of being randomly selected, right? So I want to go over the difference. So this one is independent, and part C is dependent. So I want to talk about why. So the key thing in part B is that these two women are randomly selected, right? So when you randomly select two people, it's when you randomly select people, it's reasonable to assume that the individuals are not related in any way, right? So it's reasonable to think if I randomly selected two women in the United States, they probably wouldn't be related in any way. So if they lived in the same apartment complex, they lived in the same block, they lived in the same town, like they're not related in that way, right? It seems reasonable. Where in part C, we have that the two women live in the same apartment complex, and the reason why those are dependent is because they could impact each other, right? So, for example, they could both get in the same car accident and both die, right? That would impact each other. Maybe there's a fire in the apartment complex they're both living in, right? So, one living, certainly could impact the other one. So they're not randomly selected, right? So that's an important feature if we want events to be independent, is that they're randomly selected to take away, them possibly being related. Right, so then here there's a statement about disjoint events versus independent events. So a lot of people get these two concepts thinking they're the same, but they are different concepts, right? It says here that disjoint events and independent events are different concepts. Recall that two events are disjoint if they have no outcomes in common. That is, if knowing that one of the events occurs, we know the other event did not occur, right? So in other words, what this is saying is that when you have disjoint events, there's no overlap, right? So if one of the events occurred, we know the other event did not occur because there's no overlap. So independence means that one event does not affect the probability of the other event occurring, right? So therefore, two events are disjoint means that the events are not dependent, right? In other words, so we could say that is two disjoint events are dependent. Right, so an example of this is, let's say I do an experiment where I roll a single 6-sided die. If I let E be the event that I roll an even number, right, that would include rolling a 2, a 4, or a 6. I could let F be the event that I roll an odd number, right, which would include getting a 1, 3, or a 5, right? And something you want to note is that E intersect F is equal to the empty set, which means that they're mutually exclusive or disjoint, right? Also, the probability of event E happening would equal, the number of ways E happens divided by the number of things in the sample space, which in this case would equal 3 out of 6. Right? There are 6 numbers in event E, 2, 4, and 6, and there's 6 options total. So this is just equal to 1/2. Right? Similarly, if we calculate the probability of F, this would equal the number of ways that F can occur divided by the number of possible outcomes. So same reason would be 3 out of 6, right? There's 3 numbers in F, set F, and the sample space would be 1 through 6, right? So there's 6 options. So this can reduce down. This is equal to 1/2. Right? So what we have is that E and F are mutually exclusive or disjoint. Right? But what if we knew something about event E or F? Would that change the likelihood of so in other words, if I knew something about E, would that influence the likelihood of observing F, right? And the answer is yes, that's going to happen, right? So in other words, let's say, what if, you're told that your roll is going to be even, right? Then that would mean that the probability of E is going to equal 1, right? Because I know I'm getting an even number. It's going to be 1, where the probability of F is now going to be 0, right? It can't happen because I got an even number. So in other words, the knowledge of event E changes the likelihood of observing event F. Right? So therefore, E and F are dependent. Right? So if we know that 2 events are disjoint, it also means they're dependent. You can see this is just one example to illustrate this. Right? So in this section, we're going to be looking at only independent events. In the next section, we'll look at what happens if we have dependent events. Right, so learning objective 2 is to use the multiplication rule for independent events. So we have here that if E and F are independent events, then the probability of E and F equals the probability of E times the probability of F. Right, so we could write that, using our intersect symbol, right? So the probability of E intersect F equals the probability of E times the probability of F. Oops. right? And this is if E and F are independent. Right. So in other words, knowing one of the events doesn't influence the other event. Right. So here's an example of computing probabilities of independent events. So it says the probability that a randomly selected female aged 60 years old will survive the year is 0.992. According to the National Vital Statistics Report, what is the probability that two randomly selected 60-year-old females will survive the year? So if I let event E equal the event that the first female survives, and F equal the event that the second female survives, then what we're trying to find is what's the probability of E and F. Right? That's equal to the probability of E times the probability of F, which will equal, so in this case, the probability of E and probability of F are both equal to this value, this 0.992 number, right? So this would equal 0.992 times 0.992, which equals 0.984064. Right? So if we wanted to interpret this in a sentence, we could say that if we randomly selected two 60-year-old females 1,000 different times, right? So the reason why I picked 1,000 there, so basically I just chose to maybe use the first three decimals of this number, right? So focusing on what's in that red box, right? So 0.984 is equal to 984 over 1,000, right? Because that 4, is in the thousandth spot, right? So that's how we could turn that number into a fraction. So in other words, if we randomly selected if we randomly selected two 60-year-old females and we did this 100 different times, right, we would expect both females to survive. 1 year. And 984 of the samples. Right? Because 984 of 1,000 is 0.984, which is our probability rounded to 3 decimal places. Right? So it just gives you an idea for what that number represents. Right? So then the next example is about computing probabilities of independent events. So it says a manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it's purchased. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? Right? So if we, let event D equal the event that the fitness equipment. I guess we use exercise, right? So let D equal the event that the exercise equipment is defective. And we could let maybe let F equal the event that the customer uses the equipment in the first year, right, after it's purchased. So what we're really after, right, is what's the probability that D and F occur, right? Because in order for someone to make a valid warranty claim, right, the things that have to happen is A, you have to have something that's defective. Your exercise equipment has to be defective, and you have to actually use the equipment to know that it's defective, right? So both of those things have to be true in order for you to make a valid warranty claim. So we're saying the probability of D and F happening, right? So this would be equal to the probability of D times the probability of F, right? Because these are independent events. So the probability of D is 0.1, right, given here. And then this value, 0.3, that would be the probability of F, 0.3. So we would have 0.1 times 0.3, which equals 0.03. Right, so we expect somewhere around 3% of the customers to make a valid warranty claim. Right. So then this next equation is about maybe more general sense, right? That if we have events E1, E2, E3, E3, or all the way to En are independent, then the probability of with ands in between those happening would just be equal to the probability of E1 times probability of E2 and so forth, all the way to the probability of En. Right, so we're extending it to more than just two events. Right, so like an example of that, so it says the probability that a randomly selected female age 60 years old will survive the year is 0.992 according to the National Vital Statistics Report. What is the probability that 4 randomly selected 6-year-old females will survive the year, right? So in other words, what we're trying to figure out is what's the probability that the first will survive. Oops. And that the second survives. And the third survives. And the fourth survives. Right? So we want all 4 randomly selected to survive the year. Right? So that's using this idea here in this equation, right? Is that we have 4 events in here, so this is just going to be equal to the probability of each one, be the product of each one of these, right? So the probability that the first survives times the probability that the second survives times the probability that the third survives times the probability that the fourth survives. Right, and all these would be equal to the same thing, right? Each of these individually would be equal to 0.992. So we'd have 0.992 times 0.992 times 0.992 times 0.992, which this is approximately equal to 0.9684. right? So we can extend that multiplication rule to n independent events, right? So if we had five events that were independent, we were trying to find, E1 and E2 and E3 and E4 and E5, we could just find the product of each of their probabilities. Right? So then the next problem here, so we still have that the probability that a randomly selected female aged 60 years old will survive the year is 0.992. We're asked what's the probability that at least one of 50 randomly selected 60-year-old females will die during the course of a year, right? So something that's important for you to recognize is that at least, essentially means greater than or equal to, right? So when I say at least one, I mean one or more, right? Of the 500 randomly selected females will die during the course of a year. Right? So I'm going to come up to the side so I have more room for this, right? But essentially, when you're trying to find what's the probability that at least one of the 500 females die, this would be equal to the probability that, the first person dies, or the second person dies, or the third person dies, so forth, all the way until you get to the 500th person. Right. So that would, so that would be equal to, and since these are randomly selected, they're gonna, they're gonna be independent events. Well, and also these would be mutually exclusive, right? If one person dies, that's going to not overlap with two dying and so forth. So this would end up being equal to the probability that one dies plus the probability that two people die, plus the probability that three dies, plus ... plus the probability that 500 people die. Right, so trying to calculate each of these would be very time consuming. Right, so something that we want to notice is that if you take the complement of at least one dying, right, the complement of that would mean that none die. Right, that's like the opposite, right? So if at least one person dying is the event, kind of like the opposite of that is that none are dying. Right, so knowing this, and also remembering we looked at a rule that if you have the probability of E complement, that's equal to 1 minus the probability of E. Right? We could use this equation then to solve this. Right? So we could say that the probability of at least one dies would be equal to 1 minus the complement, which would be the probability that none die. Right? So this is equal to 1 minus, so the probability that none die would be equivalent to the probability that everyone lives, right? So in other words, the first, survives the year, and the second survives, and the third person survives, and ... all the way until we get to the 500th person surviving. Right? Because none dying means that everyone lives, right? So we're just using that idea, that fact. So then each of these events, since they're randomly chosen, are independent, right? So this would be equal to 1 minus, so using, let me scroll over here. Right, so what we're using now is this multiplication rule for n independent events, right? So in this case, I have 500 events, so it's a lot, but we can apply that rule. Oops. So this would equal 1 minus the probability that the first survives times the probability that the second survives times the probability that the third survives dot 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 times the probability that the 499th person survives times the probability that the 500th person survives. So we know each of these individual probabilities, right? That's 0.992. So this would be equal to 1 minus 0.992 times 0.992 times 0.992 dot 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 times 0.992 times 0.992, where I'm going to have 500 factors of this, right? Because I have 500 spaces for people surviving, right? 500 people. So this would be equal to 1 minus 0.992 raised to the 500th power, right? Just using exponential notation. And this is approximately equal to 0.982. Right? So if we put this in words, and I'm going to think about this number in terms of 100, right? So if I just focus in on the first two decimal spots, right? 0.98 is equal to 98 over 100. So if I go to interpret this, I could say, if we randomly selected 500 females, 60 years old, 100 different times, we would expect at least one to die in 98 of the samples. Right? So I would collect 500 randomly selected females, and I would do it again, select another 500 randomly selected females. I do that 100 times. And then if I look at each of those individually, then 98 of the 100 are going to have at least one person dying, right? So maybe the first one had one person dying, the second one maybe had 5 people that died. So they're all going to be different, but 98 of them, we would expect to have at least one person dying. That's what this probability, the meaning of this probability. All right, so that's what I have for this section. Make sure you let me know if you have any questions. Thanks.